Can anyone say in the last class what we have seen? I'm sharing my screen. Yeah. Can anyone say in the last class what we have seen? Hello. Yeah, yeah. So we completed with serial adder using meal emission and mode emission. We left with one more topic, that is functions and tasks. Okay. This evening I will try to cover that functions and tasks, and we will revise the all the Verilog concepts. We will revise. Today I want to explain about this FPGA, okay, field programmable gate array. So basically, what is means what is front end and what is back end? I think you have idea. Like in the front end, you have RTL design. Okay, so in the front end, you have RTL design. RTL design means register transfer level. So basically, like we studied about the four modeling styles. Is my voice is clear? No, please confirm so that I will move forward. Hello, my voice is clear? No. Okay, okay, okay. Thank you. So see here there is a customer, and RTL design means like there is a specification. Specification means what? Means here you have like specification, like architectural engineers are there. So when you are making an IC, okay, when you are making an IC, this architectural engineers, what they will do means they will take the specification from the customer, okay, our client, okay. So that IC, so whatever the VLSI IC is there, that is used for which purpose? That means that may be used for defense purpose or computer related purpose or network related purpose. Okay. Again, they will decide how much area it will take, how much power it will take. Okay, within how much span of time we can complete whole design process. All those things will be done taken in the specification. Okay, after specification, RTL description. Okay, so RTL means a register transfer level. So as I told you in the introduction itself, what is the difference between software language and hardware descriptive language? Software languages, it will not it will not generate the hardware. Okay, they will give the application only. But hardware descriptive language, we can convert your code into hardware, okay, by using a synthesis. Okay, so we already studied about four modeling styles are there, like switch level modeling, gate level modeling, and data flow modeling, and behavioral modeling. Okay, so when you write your code in the data flow modeling and behavioral modeling, that is RTL. Okay, RTL designers will write. So whatever you studied in the digital, like a combination circuit or sequential circuit, you are describing your hardware in terms of like coding. Okay, in terms of textual form, that is RTL. Okay, so hardware descriptive language. So we already studied like there are two types of languages are there. Those are PHDL and Verilog. So mainly Verilog is easy and easy syntax is there, and it will follow the C syntax. So that's why like we are using Verilog only. Okay, for the ASIC we are using Verilog only. Sometimes FPGA they will use VHDL. Okay, very high speed integrated circuit hardware descriptive language. Okay, and next you have like functional verification. Functional verification means, as I told you, like up to some extent we can verify. We already wrote the test benches. Okay, for verifying the correctness of the design, we are writing the test benches. Okay, so we wrote the test bench for all the combinational circuits and sequential circuits and FSMs and serial adders also. We completed. Okay, up to some extent, Verilog will support. Okay, and so that means if you want to do that verification, you need to go for SystemVerilog. Okay, SystemVerilog have some more concepts, like it will support two-state data type, and some more concept will come like polymorphism, inheritance. Okay, inheritance and OOPS concept will come. Okay, like child class, parent class. Okay, and randomization will become. So here in the RTL design, we are giving fixed stimulus, fixed inputs to the design. Okay, but in the system Verilog or UVM, we can give the stimulus randomly. That too, we can give constrained randomization. With conditions, I can give the random signals. Okay, and random signals to the design. Okay, so that is randomization. Okay, and here in the Verilog we are using black box test bench. Black box test bench is whatever there in the design we don't know. Okay, after getting from the design we can find out the bugs. Okay, but in Verilog in system Verilog we are using white box testing. White box testing means we are using like a concept called assertions. So we can include the assertions in the design so that in beginning only we can find out the bugs. Okay, in the beginning only so that we can we can save our time now. So after means when you are using Verilog, after 1,000 time units, after 1,000 time units, you are getting the you can find out the bug by using simulation. But initially itself, we can find out the bug. That is in the by using assertions. Okay, so you will give some mathematical formulas in the assertion so that you can find out the bug within the beginning itself. Okay, and you are going for UVM also. So system Verilog is robust. That means if you are writing the test bench for I2C, mainly our motto in the system Verilog and UVM is you are developing the test bench. You need to verify. Verification engineers will verify the correctness of the design. Okay, RTL engineers will write the code in the either Verilog or system Verilog or VHDL. Okay. So next, what happens here? UVM is UVM means in the functional verification you will get a system Verilog and UVM. Okay. So system Verilog and UVM is it's not a language. It's a universal verification methodology. So by using system Verilog, when you are writing the test bench for SPI, if you want to write the test bench for I2C or UART or dual port RAM, so from the scratch you need to develop the test bench. Okay, but by using UVM, what you can do, there are already inbuilt objects will be there in the library. Okay, so you can register that library. Okay, so that means you can reuse. Reusability is there in the UVM. Most of the companies they will use UVM only. Okay, so that will comes under the verification. Mainly in the verification, we are using system Verilog and UVM for verification the correctness of your design. Okay. After that, logic synthesis. Logic synthesis means like you have some constraints like ATP, area, time, and power. Okay, the synthesis engineers will work under these constraints: area, time, and power. Okay, so I told you now after synthesis it will generate gate level netlist. Okay, gate level netlist and logic equivalency chess. This is logic design. Okay, logic design and physical design means they will take the input from the physical design and they will do place and road physical layout and physical verification. After that, GDS2 file will be generated, graphical database system. Okay, that GDS2 file is given to the fabricators. So fabricators will fabricate this design. Okay, so this is our not our main thing. So mainly we are discussing about RTL design. The two RTL mostly about to complete. Is it fine? Any doubts or queries in the VLSI front end and back end? Shall I move forward? Waiting for your response. Anyone? Give response. Is it fine? Is it clear? Any doubts or queries in this? Okay. Yeah. So this is VLSI front end. Basically, FPGA design means this is FPGA design flow. Actually, design entry and behavioral simulation. Okay, HDL you are writing and you are simulating with waveforms. Okay. If it is not okay, again you go to the design entry. Okay, constraints I told you know area, time, and power. That will go to the constraints and synthesis. Okay, and synthesis after that translate. You need to convert your code into this gate level netlist mapping. Mapping means which board you are using, okay, which FPGA board you are using. So you need to map to that technology mapping, okay, functional simulation and static timing analysis will come. Static timing analysis means like you will study about this setup time, hold time, and propagation delay, clock tree jitter, all those things. So like delay related elements will be done in the static timing analysis. And here you will get a place and route. and the bit generation. So bit file generation will be done. That means in terms of X file, we'll generate the bit file that we are programming into FPGA, and FPGA will be worked as based on your requirement. Suppose if you want to design FSM, okay, you'll write the code for the FSM, and these all steps you need to do, and after that you will generate the bit file. That bit file you are loading in the FPGA. Is it fine? FPGA based design flow. Okay. So FPGA same thing. FPGA design flow. Okay. Design specification, behavioral description, RTL, that is HDL, functional verification and logic synthesis, technology netlist, placement and route, bitstream generation, and programming your code into the FPGA. Okay. So so same thing. Whatever design specification means, what design specification means, we consider the what the design says. Okay, we go to the requirement of the situation. Okay, so that is design specification. And behavioral definition means we are writing the behavior of the hardware. Okay, programming language. As I told you, there are two HDLs are there, like VHDL and Verilog. VHDL is very high speed integrated circuit hardware descriptive language, and Verilog HDL. Okay, so VHDL means like two input AND gate is there. We can write with this VHDL. Inputs are A, B, and output is Y. And this is with Verilog. Okay, non-blocking with A and B when you are using behavioral modeling. VHDL means it have inputs, outputs are specific. So whatever the inputs, outputs. So this is Verilog. Actually, this is Verilog, not VHDL. We are writing in terms of behavioral model. Okay, always at the red star. We already seen the code. Okay, always at the star begin. Okay, I need to declare input A comma B, output range Y. Okay, and begin Y equal to A and B. Okay, bitwise operator and B. Like this, we need to write. Okay, and in VHDL, basically like for inputs and outputs and inouts, specifically we need to declare in the entity, and behavior for the hardware will be done in the architecture. Okay, so we can do for behavior of the hardware by using three structural modelings. One is structural modeling, behavioral modeling. Behavioral modeling means what? With the help of truth table, we need to write the behavioral modeling. Data flow modeling means with write up extra expressions. Okay, same thing we seen in the Verilog that will come in the VHDL only. But here we are using symbols. Here we are using some predefined and or like that we are using. And entity we are declaring the inputs, and in the architecture we are writing the code. Okay. Actually, in Verilog we don't have entity and architecture, but we have module. As I told you in the starting, we need to write the Verilog code from the module, and it should end with end module. Okay. So y equal to what? A and of B. A logical and of B. Like this we need to write. Okay. So RTL. What is RTL? Your program will be converted into RTL. I told you, no, register transfer level. Your program will be converted into register transfer level. Internally, like there will be some gates and nets, and there are some D flip flops are there. Okay, how the data is transmitting through the registers is nothing but RTL. Okay, so that is RTL, register transfer level. Okay, and functional verification. Functional verification and testing means here the errors are verified. Once it is correct, next step is to verify the input and output. Okay, functional verification means what? Compiling. Okay, you are compiling whether you are like after writing a code, you need to do the simulation. No, so that means here you are verifying any errors are there or not. Okay, so if any errors are there, you need to verify and you need to go to the next step. Okay, and next is logic synthesis and technology mapping. Okay, so we will synthesize the logic circuit, and technology mapping means you need to map to what FPGA board we are using. So mainly we are using Artix, Altera, and Vertex, all these things we are using. Okay, this type of boards we are using in the FPGA. Okay, and in technology mapping, particular board is going to select, and then IO mapping should be done. As I told you, no. So in the technology mapping, we need to select the board, and based on that board, we need to map the IOs. Okay, and the technology next list means netlist corresponding to selected input mapping will be created. Okay, selected mapping, the inputs will be created. Okay, and placement and routing means required a number of logic elements are selected and interconnection. Okay, so we need to select the required amount of logic element. What are the required number of logic elements, and we need to select, and we need to do the interconnection. Routing is interconnection. Okay. Bitstream means the file supported by FPGA board to dump into it. So mostly that will be stored in .bit file. Okay. So .bit file it is a hex file only. Okay, it's the one type of hex file only. As in the BTech also you studied like microcontroller. Okay. Suppose microcontroller, you have a kit and you have a peripheral device. Okay. So suppose if you are interfacing, example like interfacing LCD. So you are writing the program for the LCD in the in the assembly language or embedded C. At last, what it will do? It will generate .x file. That .x file you are loading in the your microcontroller. Based on your application, your microcontroller will work. Okay. Same like that, here you are generating the bitstream. The bitstream you are loading into the FPGA. Suppose if you want to if you want to construct a decoder. Okay, decoder. So FPGA will work as decoder. After that, if you want to design some FSM logic. So the decoder logic will be erased, and after programming, this decoder logic will be erased. Again, your FPGA will work as a this FSM. Okay, mostly this the FPGAs consist of SRAM. SRAM means you know that RAM is volatile. Okay, so when the power is cut down, what happens? Total data will be erased. Okay, so that continuously it should be in a what mode? In a power on mode. Okay, as CPLDs will be made with ROMs. Okay, those PROM. Those are non-volatile. Even though power is switched off, the data, whatever the program is there, that will be present in the CPLDs. Okay. I think in BTech you studied about this PLDs, PLA, PROM, PLA, PAL, CPLDs, and FPGAs. Okay. This is field programmable gate arrays. Okay. Dumping. So now cable is connected between the system and FPGA board. After dumping it, shows done on the board. Okay. So this is total FPGA flow. Is it fine? Do you understood? Any doubts or queries? Shall I move forward? Please give response so that I will move forward. Okay. So thank you. Okay. Yeah. Okay. What about others? Yeah. Yeah. Okay. Thank you. Next, basic architecture of FPGA. Okay. So if you see the basic architecture of FPGA, so FPGA consists of this logic blocks. Okay, basically it consists of logic blocks and switch blocks. These are switch blocks, and these are interconnects. Okay, interconnects, and switch blocks are connected through the interconnects, and there are I/O pads. These are I/O pads. Okay, so I/O pads are symmetrical in nature. Okay, suppose one side is there means you need to connect like this. No, so all sides are there means from here you can connect inputs, from here you can connect outputs, you can connect in outs, like that it is symmetrical in nature. All sides there are IO points. Okay, this is the basic architecture of FPGA. So basically it consists of how many elements? One is logical, four elements will be there. Logic blocks and switch blocks, interconnects, and IO pads. Okay, switch blocks, interconnects, and IO pads. Okay, so see here, FPGA consists of IO blocks or IO pads. These are IO blocks or IO pads. Okay, these IO blocks are IO pads. Okay, and next you have CLBs. The switch blocks are there, no? The switch blocks are CLBs, configurable logic blocks. Okay, and next you have interconnects. These are interconnects. The switch blocks or configurable logic blocks will be connected with interconnects. Okay, interconnects, and there is a switch matrix. Okay, switch matrix will be there. Okay, switch matrix. Okay, IO blocks. What are IO blocks? IO blocks is easy to communicate with the external device. Suppose if you want to connect some external peripheral, you need some IO blocks, no? So input output blocks that you need, okay, to the FPGA. Okay, so we can connect with the external device to this IO block, and whatever the data is there, the data will be transmitted and taken from the external source. Okay. So these IO blocks are surrounded by the FPGA. Symmetrically it will be there. Okay, all sides the IO blocks will be there. Okay, all sides the IO blocks will be there. And next, I told you, no, CLBs. Okay, configurable logic blocks. Configurable logic block means basically configurable logic blocks consist of lookup tables. LUT is lookup table, and flip flop. This is D flip flop, and there is a mux. Okay, so the output of the mux, depending on the selection line, it can get directly from the lookup table, or it can be get the output of the D flip flop. Okay, depending on the selection line. Okay, so there is a reset logic for the D flip flop, and clock will be there in the D flip flop. Okay, suppose if you want to design a combinational circuit. Okay, the combinational circuit will be designed in the lookup table. That combinational circuit output is coming through the output. Okay, coming through the mux, and it is coming through the output, so that we can design any combination circuit, like decoder or comparator, half adder, full adder, like that. Any combination circuit you can design by using lookup table. Okay, so how many inputs are possible? So that means four inputs will be possible for the lookup table. This is one CL. Okay, and suppose if you want to design a sequential circuit. Okay, sequential circuit is means it's a combination of combinational circuits and flip flops, no. Okay, combination circuits and flip flops. Okay, so combination circuits are designed with the lookup table, and a flip flop is designed by using D flip flop. Okay, so whatever the sequential circuit is there, that will be designed by using D flip flop, and both combination, it is coming through the output. So by using this lookup table, you can design any combinational circuit or any sequential circuit. Okay, is it fine? Do you understood? Okay, so this is basic configurable logic block. Okay, configurable logic block. Okay, so see here, CLB is a fundamental block of FPGA. This is the heart of FPGA. Okay, we can say that this is the heart of FPGA. Okay, we can also say it is the heart of FPGA. Okay, because logic function is implemented in the CLB. Okay, so whatever the logic function is there, logic function means in the digital we see in each and every module, each and every combinational circuit or sequential circuit what we designed. Suppose example, you take half adder. Half adder, you draw the truth table. After that, you draw the K map. From the K map, you got the logic expression. For every combination circuit or sequential circuit, you got the logic expression. Okay, that logic expression will be developed in the implemented in the CLB. Whatever the logic expression is there, even though sequential circuits also, like for JK flip flop or counters, shift register, there will be some logic expression. That logic expression you are developing in the lookup table. Okay, so it consists, CLB consists of what? Four input LUT, lookup table, D flip flop, and mux. Four input LUT, D flip flop, and mux. Okay, so four input LUT is a logic element where the logic function is implemented based on the truth table. As I told you, no. Suppose if you want to design a decoder circuit. Okay, so decoder circuit means logic. So first you will draw the truth table. From the truth table you will get the logic expression. No, that logic expression will be done in the lookup table. Okay, logic expression will be done in the lookup table. Okay, logic implementation. Okay, implementation will be done in the truth lookup table. Okay, okay, lookup table, and D flip flop is there. D flip flop is used to provide the delayed version of output. As I told you, know, you are getting the output through the lookup table or through the delayed version of D flip flop. So D flip flop, I told you, like D flip flop is a delay flip flop, or it's a sequential buffer. Okay, so whatever the input you are giving, you are getting the output with some delay. Okay, that's why we call as delay flip flop. Okay, so you are getting the output as a delayed part. Okay, so this is the output of the mux. Okay, and next mux. Mux is having two inputs, so it is either to select either a direct output or delayed output of LUT. So you can select a direct output of LUT or delayed output of LUT. Okay. Is it fine? LUT. Any doubts or queries in this? Shall I move forward? Waiting for your response. Okay. Thank you. Okay. Next you see, this is lookup table. This is lookup table. Sorry, this is CLB, configurable logic block. And next, interconnects. Interconnects we already seen, no? What are these interconnects? This configurable logic blocks are connected with the interconnects. Okay, these interconnects. Okay, so how it is connected with the interconnect? Interconnects are used to connect the, I told you, no, configurable logic blocks. Okay, here what it is indicated. Here it is indicated as a switch blocks. Switch blocks are CLBs, both are same only. Okay, so interconnects are used to connect the configurable logic blocks. So that can be connected horizontally or vertically. Its main purpose to transfer the data among the CLBs. Okay, yeah. So in order to transfer the data between the CLBs, interconnectors are used. Okay, uh, so interconnects are separated over the entire board to access or transfer the data easily. Okay, so to transfer the data between these each and every CLBs, we are connecting these interconnects. Okay, suppose if I want, so maximum how many inputs I can connect to one CLB? Four inputs I can connect to the CLB. Okay, suppose if I want eight inputs. Okay, so I will use two CLBs. Two CLBs are connected through this interconnects. Okay, so like this I can design any module. Okay, so this is about the interconnects and switch matrix. Okay, switch matrix means here this is switch matrix is there, no? Switch matrix. Okay, so this is a switch matrix. Interconnects, how it is connected means there is a switch matrix. Okay, switch matrix. Uh, so inside, inside the switch matrix, like this will be there, like this dots will be there. Okay, so each dot again it is in terms of like this. Each switch matrix point to six routing switches. Okay, this is six routing switches. Okay, six routing switches. Uh, so that means it is vertical and horizontal. So suppose like if you want to connect this one will be fused. Okay, like this one and this one. Second and this line will be fused. Okay, so switch matrix. This switch matrix will be like each pass transistor, NMOS pass transistor will be there. Okay, NMOS pass transistor and middle one more pass transistor and in middle total six pass transistors will be there. Okay, when this is connected, so high signal is given to this NMOS circuit, so that this becomes on. This becomes on. Okay, so like this switch matrix will be developed. Okay, suppose see here. Suppose if signal should pass from N to north to west, north to west. Okay, so this will be on, and the signal will pass from north to west. Suppose signal should pass to north to south. Okay, so you need to give high signal to this NMOS transistor, and signal will be transmitting from north to south. Okay, like this we can connect the switch matrix. Okay, and see here. Switch matrix is used to connect the horizontal and vertical line segment. Whatever the horizontal and vertical line segments are there, that are used to connect the switch matrix. Okay, and uh, six. Uh, one second. I keep charging. Okay, so here. So six pass trans. I told you, no. Switch matrix consists of six pass transistors are used for this purpose. They will get input from the memory cells. Okay, from the memory cells. Suppose here, let us take this is one, this is zero, this is zero, 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 and one. Okay, so which one is connected? Here you are getting the one. Okay, one signal. So one signal means this will be this will be on, and here one signal you are getting. So this will be on. Okay, so like this, switch matrix will be connected. Okay. So FPGA technology, if you take FPGA technology, FPGA will use three types of technology. One is SRAM technology, as I told you, no. Mainly FPGA will be use this SRAMs. Okay, and anti-fuse technology and EEPROM technology, EEPROM technology. Okay, this will discuss. So if you see SRAM technology, Whatever the configurations are there, that will be storage on the SRAM cell. Okay, static RAM. S is nothing but static RAM. Static RAM means basically it consists of a latch. Okay, two flip flops connected back to back, and one more pass transistor will be there. Okay, one more pass transistor, two pass transistors will be there. Two NMOS transistors will be there. So just to go through that SRAM cell, SRAM is volatile. So volatile means what? When the power is gone, so whatever the code is there, that will be whatever this data is there, that will be erased. Okay. So basically, like latch is connected with two inverters, no? So one inverter is designed with two CMOS circuit, one CMOS circuit, one NMOS, one PMOS and one NMOS. PMOS has pull up and NMOS has pull down. So like that, two inverters are constructed with four transistors, okay, two CMOS circuits and two more pass transistors. Total six transistors are required to develop the SRAM cell. So this will occupies a large area, and this will allows dynamic and parallel configuration. Okay, and so see here, this consists of what, as I told you, two CMOS inverters are there. So two CMOS inverters connected back to back. Okay, with a pass transistor. Two more pass transistors are there. Okay, so one more pass transistor will be there. So there is a word line. Okay, word line is coming. When word line is one, this pass transistor will be shorted. Okay, so we can means we can write the data or read the data from the memory cell. Okay, when word line is equal to one only, this transistor will be on, and we can write the data into the memory cell, or we can read the data from the memory cell. Okay, when word line equal to 0, so this transistor will be in off state. Okay, so this is a CMOS inverter circuit and SRAM cell. So this is the basic 60 transistor, 60 transistor. As I told you, no. So these two inverters are there. No? Basically, inverters are constructed with the CMOS circuits. PMOS as pull up and NMOS as pull down. Okay. So this input is connected to this output. Okay. This input is connected to this output. This input is connected to this output. Okay. Back to back. This output is connected to this input. Okay. So this output is connected to this input. Again, two pass transistors are there. This is given to the word line, and from the bit line, data will be read or write into this SRAM cell. Okay, so this is basically 60 SRAM cell. Okay, so advantages. What are the advantages? It can be easily programmed, and it can be easily reprogrammed during the system operation, providing dynamically reconfigurable system. And circuit used in SRAM can be fabricated with standard VLSI process. So whatever the circuits used in SRAM, by using VLSI standard process, we can design. Okay, these are the advantages of SRAM set. Okay, SRAM related FPGA. And FPGA anti-fuse technology means what? Anti-fuse means like actually there are drawbacks of SRAM. Okay, what are the drawbacks? Power consumption even when the program is not changing. There will be some power consumption is there. Okay, uh, and whatever the bits in SRAM cells are susceptible to theft. Okay, so there can be chance of means varying the bits. Okay, and this is volatile. Volatile means as the power is switched off, total data will be erased. Okay, so based on this drawback, we can go for anti-fuse technology. Actually, what is fuse technology? Initially, when it is connection established, that is fuse. Okay, in your household applications, in your household, there will be fuse. No, in stabilizers also you have fuse. Okay, so when fuse is there, then you will getting the supply. Okay, if fuse is not there, what happens? That will be disconnected. Suppose high power is coming, high power enters. What happens? That fuse will be disconnected. So that when you connect stabilizers, so it will avoid the damage of high electronic gadgets like smart TV or fridge. Okay, so that fuse cost less only. So compared to that fuse, these are costly, no? So that we can connect this stabilizer. Okay, as high power enters, what happens? These will be disconnected. Okay, so this is fuse technology. Okay, what is anti-fuse technology? Anti-fuse means what? Initially, it will be fused. Okay, initially it will be fused. Initially it is connected to between the two metals. When you apply some voltage, it becomes antifuse. Okay, when you apply some voltage, it becomes antifuse. That is antifuse technology. Okay, so antifuse is one time programmable. Means what? Once the program is written, so that is not changed. One time programmable. So fuses are permanently put in the place. So a link is established when the current passes through it. Okay, programming is very slow because each antifuse must be programmed separately. So each antifuse we need to program separately. So programming becomes very slow and small area and non-volatile. Non-volatile means even though the power is shut down, so your data will be there in the antifreeze technology. And irreversible. Okay, uh, irreversible means any errors are coming in the design, we can't correct. Okay, once the program is written, so permanently it will store. Okay, this is antifreeze technology. uh, so antifuse means what? Initially connection is not there. When current passes, connection is established. Okay. Initially connection is not there. Okay. Advantages: non-volatile, delays due to routing are very small, low power consumption. Uh, so there are some problems in the SRAM technology, theft problem. So that theft problem can be overcome in the antifuse technology. Okay, theft problem can be overcome in the antifuse technology. And disadvantages: it require very complex fabrication process and a separate external setup will be required. External program is required to program or configure the design, after which design cannot be changed. Okay, and so we already seen SRAM technology volatile, antifreeze technology reprogramming is not possible, and next you have EEPROM technology. Here complex fabrication process, antifreeze technology. Uh, and next EEPROM or EEPROM. EEPROM or EEPROM means electric erasable programmable read-only memory or electrically erasable programmable read-only memory. Okay. So switch is disabled by injecting the charge on the gate using high voltage between the gates and drain. Okay. And the charge is removed by UV light. Here you are using UV lights for the program. Okay. So that whatever the programming parts you want to do, that programming parts you need to expose to UV light. Okay. And this is non-volatile and slower programming is that. Slower programming. Okay. So you need to expose that whatever the programming exposed to the cells, whatever the programming into the UV lights. Okay. So so advantages: no external permanent memory is needed to program it power up. Disadvantage: extra processing steps is needed, and static power loss due to pull up resistors. Okay, which is high resistance. Okay, there will be static power loss will be there in the EEPROM or EEPROM. Okay, these are the disadvantages. Okay, and coming to FPGA families, is this fine? These technologies are fine. Please give response so that I will move forward. You have three technologies like SRAM technology, antifuse technology, EEPROM technology, and EEPROM technology. Okay, okay, thank you. Thank you. Next, see here. Next, FPGA families. FPGA families, if you see, FPGA families, you have four types are there: Ultraflex, Spartan, Vertex, Artix. Okay, Ultraflex and Spartan, these are low performance families, and these Ultraflex and Spartan we are using in the laboratory purpose only. Okay, Vertex, this is used for high performance family and industry level. Artix is a moderate family and lab purpose only we are using. Okay. Spartan is a Xilinx. Okay. Spartan is the family coming from the Xilinx. Those are XC4000, XC5000. Okay. So old families are there like XC3000, XC4000, XC5200. Okay. This will use the old technology like zero point 0.5 micrometer means what? 500 nanometer technology. Okay. 350 nanometer technology, 250 nanometer technology. Okay. Like what is technology? Technology means you studied about MOSFET, no? So MOSFET, the distance between the source and drain is a channel length. The channel length is we are working under 2 nanometer technology. Okay. Nowadays we are working under 2 nanometer. The transistor size will be 2 nanometer. The length of the channel will be 2 nanometer or 3 nanometer. Okay. So this 500 nanometer, 350 nanometer means this is olden. So this is not recommended for modern design. Okay. So high performance families are Vertex, Vertex E, Vertex 2, Vertex 2 Pro, Vertex 4, Vertex 5, Vertex 6. Okay. Uh, so here it will be like 100 nanometer, 130 nanometer channel length. I told you, no, channel length. So the distance between source and drain is 0.13 micrometer. Okay, 130 nanometer. Okay, these are the Vertex families. Okay, low cost families are Spartan. So Spartan XL, Spartan 2, Spartan 2E, Spartan 3, Spartan 3E, Spartan 3A. This will follow like 180 nanometer and now 90 nanometer and 90 nanometer optimized. Spartan 6 is 45 nanometer. Okay. So this Spartan are used for lab purpose only. Okay. And this is Altera. Actually, any FPGA family, the architecture is same only. So previously we already seen, no, where we are seeing the architecture. Here we are seeing the architecture. Okay. So the architecture will be same only. Just this is the basic architecture for any FPGA family. Okay. So it consists of CLBs, configurable logic blocks, interconnects, switch matrix. Okay, switch matrix, interconnects, switch block, and IO blocks. Okay. So if you see this, what do we call? Mm, yeah. See here. Ultraflex 8000 FPGA top architecture family. So it consists of IO elements. These are IO blocks. These are IO blocks. Okay. These are interconnects. These are interconnects. Okay. And here CLBs are logic elements. We call as logic elements. Okay. CLBs are logic elements. Okay. Or logic array blocks. Labs. We call as labs. Okay. Again, internally CLB consists of what lookup tables, mux and D flip flop. D flip flop and mux will be there internally. Okay. So there we'll call as configurable logic blocks, but here we'll call as logic elements or logic array blocks. Okay. So basically these are interconnects. So this is the architecture of Alteraflex. Okay. So CLBs I told you, no, CLB is named as LA lab. Lab means what? Logic array blocks. Okay. Lab consists of 8 logic elements. Okay. Each logic element consists of 4 input LUT and D flip flop and mux. Okay. Each lab consists of how many lab elements? Lab elements means CLBs. Okay. So 8 lab elements. Each lab elements consist of what? Four lookup tables, D flip flops, and mux. Okay. And interconnects are connected with horizontal line and vertical. These interconnects are there, no? These are connected with horizontal line and vertical line. Okay. And this is Xilinx XC4000. So it consists of IO buffers, IO blocks, and switch matrix. Okay. And CLBs, configurable logic blocks, and interconnects. Okay. So like this, same as our architecture, it will look like. Okay. Again, so this is actually XC4000 CLB, internal structure of CLB. Okay. As I told you, like each CLB consists of configure lookup tables. Here, lookup tables means we call as functional generators. Okay. So three functional generators are there: G, F, H. Okay, and these are connected with D flip flop and mux. Here, one more D flip flop is there, and one more mux is there. Okay, so like this it is connected. So XC4000 consists of CLBs, local or global routing, IO buffers, and SRAM based memory configuration. So XC4000 will support SRAM based memory configuration, and each CLB consists of lookup tables, multiplexers, registers, path for control signals. Okay, and here each CLB is divided into like G, H, F. Okay, see here G, H, F. So each function generator provides 5 delay respective of logic functions. Two functions generators are F and G can generate array logic, that is 4 inputs, but H function generator can generate logic function of 3 inputs. Actually, here G and F and G is there. No? F and G will produce 3 inputs, but H will produce 3 inputs. Okay. F and G will take the 4 inputs. Okay. It will inputs are coming as 4, but inputs to the H are 3 only. Okay. 3 only you are getting. Okay. So like this. So, but H function can generate the logic function with it can generate the logic function with three inputs. Okay, by seeing this diagram, you can analyze. And this is Xilinx pattern to FPGA. So you have delay local loops and 46-bit, 406 bits. IO blocks will be there, and inside there will be CLBs, configurable logic blocks. Okay, and so each of so here like quadrant will be there. CLBs are designed like a quadrant. Each of four quadrant CLBs uh, are supported by DLL, bounded by 406 bits block RAM. Okay, this is 406 bits RAM, bits RAM. Okay. So peripherals of chip is fixed with IOB. Each CLB contains four logics organized as pairs slices. Okay, it is will be slices. Each logic cell same as CLB only. Four input lookup table, and it consists of 16 cross 1 RAM or 16 cross 2 RAM or 32 cross 1 RAM cell. Logic for array control and D flip flop. Okay. So this is the basic diagram for Spartan 2. This is the Xilinx Vertex FPGA, high performance FPGA families. It can support up to the technology 220 nanometer to 45 nanometer. This type of FPGA families are used in industries only. These Xilinx Vertex are used in industry only. This is a focus on level integration, amount of embedded memory, performance. Some FPGA devices will be consist of both FPGA as well as the embedded, like my consist of ARM processor also. Okay, so that board we can use for both this FPGA related design or embedded related design. Like Zinc board is there. Okay, mm. So this is Vertex FPGAs, CLBs, IO blocks, and block select RAM provide 18 kilobyte storage element, and multiple blocks are there. Okay, so this is the basic diagram for overview of architecture of Vertex FPGAs. The DCS are the digital clock manager, provide self-calibration, fully digital solution for clock distribution. Okay, general routing matrix. GRM is an array of routing switches. Inside there will be GRM. So this is about the FPGA families and all those things.